Okay, so let me welcome you to this lecture 6 of our course on reinforcement learning. We are going to continue our discussion of deterministic problems and approximation in value space. But today we're going to focus on multi-step lookahead. And then after we do that, we're going to go into constrained rollout where there are constraints on the trajectory that's generated by the system. And then we are going to apply constrained rollout to discrete optimization problems like integer programming problems. So here's the outline. We're going to look at multi-step lookahead in the context of approximation value space for deterministic problems. Deterministic problems are nice in this context because they do not involve any Monte Carlo simulation. Approximation value space can be done in flexible ways that are not available for stochastic problems. So we're going to look at the case of multi-step lookahead. And today I'm going to talk about some new ideas that have not been presented before. And I think they're interesting. And they are also very fruitful grounds for you to look in terms of your mini research project, your term paper. Then I'm going to talk about constrained rollout and applications in discrete optimization. So let's get into deterministic problems and multi-step lookahead. Now, here's a picture that we have seen before, except that it is simpler. It is for deterministic problems, and it involves multi-step lookahead, truncated rollout, and terminal cost approximation. This is the alpha zero architecture or related architectures that we have seen, but it's deterministic. And it involves, at the current state, to choose the control, we form a lookahead tree that extends to L steps. Now, L is equal to 2 here, 2-step lookahead. And then from each of the leaves of this tree, we run a base policy, a deterministic base policy, and we possibly truncate the steps of the base policy and approximate the future by using a terminal cost function approximation J tilde. So we have seen this before, and one special case is where there is no rollout in the middle. We go from the leaves, we evaluate the leaves of the lookahead tree by using J tilde without any intervening rollout. Now, this is a general form of multi-step approximation in value space. Essentially, it's possible, always possible, to get this truncated rollout portion to lump it into the terminal cost approximation. And we are going to focus on this type of scheme. We're going to neglect the effects of truncated rollout. They're going to be there, except but indirectly. Now, another special case, which we're not going to consider very much in this lecture, except when we go into constrained rollout, is when the rollout is run all the way to the end. There's no truncation, and there is no terminal cost approximation. So that would be pure rollout. These two are special cases, but we're going to focus on the first one. Now, here's something that we're going to take as a fact. We like long look ahead. We think that longer look ahead is going to improve performance. This is borne out by many studies, including AlphaZero. AlphaZero owes its success primarily to this very long look ahead that it uses, like 20 moves ahead, 30 moves ahead. It's been a big contributor to the success of AlphaZero. Generally speaking, the longer the look ahead, the better the performance. Now, mathematically, this is not always true. There are artificial examples where we can show that the longer look ahead leads to worse performance. But these examples are artificial. They don't occur in practice that I know of, okay? They occur very rarely, and they are not being seen in practice. So we're going to believe the statement, and we're going to aim for longer look ahead. On the other hand, there is a constraint here, a difficulty. Longer look ahead costs more in terms of computational resources. And given that this is an online play algorithm, there are some strict constraints as to how much time we can use to generate the best move here. It may be that we have seconds, or it may be that we have hours, but there is a constraint on the time that you can use for all this operation, and the longer the look ahead, the more it costs. If we can cut down somehow on these operations here, we may be able to go longer. And that's an idea that is going to come up in what follows in this lecture. Now, our strategy is to expand the look ahead as much as possible, as much as the computational budget allows. We have some time available to compute this, to apply this multi-step look ahead, be it second or be it hours, and we are going to search as long as we can, as long as are within the constraints of our computational budget. And one idea to extend the look ahead is truncated rollout. Okay, we have discussed this before. We can view truncated rollout as a cheap extension of the look ahead length. This is also look ahead, but it costs a lot less than this look ahead. This look ahead is done with a single policy, and this policy is deterministic. So there's no Monte Carlo simulation involved. It's a very, very quick operation with a single policy. This minimization here involves all the policies available within this time horizon, so it costs a lot more. So truncated rollout is a cheap extension of a cheap way to extend the look ahead length, and that's an important idea in this context. And here's another computation saving idea that we're going to discuss. The more leaves, the more there are in this tree here, the more the computation burden increases. So an idea here is to selectively prune the look ahead tree. As we go on, drop some of the branches that do not look very promising. So now let me get into the specifics of all this. Are there any questions? Okay, so now let me redraw this look ahead, multi-step look ahead picture. Instead of going in this direction, I'm going to go vertically. So let's try to understand this figure. Here's the current state. We are looking L steps ahead. These branches here correspond to controls. And at each layer, there are states. In layer 1, there are the states that are 1 step ahead. Layer 2, 2 steps ahead. And so on. At the typical layer N, these are the states N steps ahead. And the terminal states, as far as our look ahead is concerned, is layer L. And then at layer L, there's a cost function approximation, a terminal cost function approximation. And this J tilde here may also involve a heuristic, may also involve truncated rollout, but we're not going to focus on that possibility. We're just going to assume that there's a general J tilde waiting for us at the end of L steps. So the way multi-step look ahead and approximation in value space works is to obtain a trajectory from the current state to one of the states in layer L that minimizes the shortest distance from xk to xk plus L plus the terminal cost approximation. So there are many candidates here on layer L. We need to calculate all the shortest distances from xk to each one of those. That's a shortest path computation. And then we can add to all of those the j tilde value, and then obtain the best one, and then consider the trajectory corresponding to this to the shortest distance. And we use the very first move from xk to xk plus 1. And that's all we have to do at stage k. At stage k plus 1, we're going to go to this state, then repeat the same thing, do all the shortest path calculations, terminal cost approximation, and so on, and obtain xk plus, and then obtain the, and then repeat the process. So there's a lot of computation for just one move, but this computation is fairly cheap, and we like to do it with long look ahead. Now, how do we solve the shortest path problems to all the states? We can do backwards dynamic programming. Start from layer L, and then go one step back, and so on. Compute the shortest distances from layer L, and then layer L. These are used to compute the shortest distance, well, layer L minus 1, and then the shortest distance to typical layer N, all the way to the end. That's backwards dynamic programming that we already know. But there is another alternative here, which turns out to be more convenient in the context of multi-step look ahead. And this is a forward dynamic programming. The backward dynamic programming goes from the end backwards one step at a time. The forward dynamic programming starts from the beginning and goes forward one step at a time. And at each step, calculates the shortest distances from xk to the various states in the various layers. Now, I'm going to explain this algorithm in the next slide, but basically the idea is it's not different. It's the same backwards dynamic programming, except we reverse the direction of the arcs. Instead of the arcs going forward, we have them go backward. So the end becomes the beginning, and the beginning becomes the end. And from the end, we go this way, and that's the forward dynamic programming algorithm. So I'm going to explain this in the next slide. Okay, so this is the forward dynamic programming algorithm. And this is the same figure that we had before. This is the current state, except that to simplify the notation here, the current state is called the x0. The states at layer 1 are called x1, x2, and so on. Just to make, not to carry too complicated indices. And we want to calculate the shortest distances from x0 to the last layer. So we first calculate the shortest distances to the first layer, then the second layer, then the typical layer n, and we use these to calculate the shortest distances of all the states in layer n plus 1. And the formula is what you see here. The shortest distances to states at layer n plus 1 are obtained from the shortest distances to states at layer n by doing this dynamic programming type of calculation, which involves the shortest distances to the nth layer, plus the costs of going from the various states in the nth layer to the state xn minus 1. So to do this calculation, we take the typical state at layer n plus 1, this xn minus 1. We look at all the predecessor states at layer n, take the cost of these transitions, and add them to the distances, the dn of xn of the predecessor states. And we find the best one. So we have a shortest distance from here to here, plus the cost, and we calculate all these various ways of going to xn plus 1, leveraging the shortest distances that we have to layer n in order to calculate the distances to each one of these states, xn minus 1 at layer n plus 1. Actually, this is exactly the backwards dynamic programming after we have reversed the direction of the arcs, and the beginning has become the end, and the end has become the beginning. So now, once we solve progressively these shortest path problems to layer n minus 1 to layer L, then we have obtained the shortest distances to the states at layer L. We add the terminal cost approximation, and we find some state XL star, and then we look at the shortest path that leads to xn star and move and make the first move, select the control that corresponds to the first move along this path. Are there any questions here?
There's one question.
Yes.
So is XL star chosen at layer L, like at the end of the process? And before that, every state is expanded into, right?
Yes, before that, every state is expanded, and we reach all the states here at layer L, and we find the one, this XL star, that minimizes the distance plus the terminal cost.
Okay, thank you.
Okay. So now this brings up an interesting idea, the idea of iterative deepening, whereby we find, we solve n layer problems, and then we solve n plus 1 layer problems if we have time. If we don't have time and we reach the end of our budget constraint, then we just have solved the problem with smaller lookahead. So that's iterative deepening. Solve the n-step lookahead problem before solving the n plus 1 step lookahead problem. And this dovetails with this forward dynamic programming algorithm. And now we have an anytime algorithm, an algorithm that returns a feasible solution, even if it is interrupted in the middle because we have reached our budget constraint. So in connection with iterative deepening, we choose a very long horizon and just keep going and going and going and going for as long as we have time. And then at the moment when we've reached the end of our budget, we stop the computation and find the corresponding state, XL prime, okay, some other, and we find the corresponding trajectory and take the first move along this trajectory. Okay, so this is one idea that is useful in this context. Forward dynamic programming combined with iterative deepening. Now we're going to introduce some other ideas to enhance economizing on computation. Tree pruning, okay? In tree pruning, we disregard some of the states in the process of the computation because on the basis of our interim results, they're not very good. They're not very promising. So these red portions here are what we prune. And as we prune, we have to deal with a thinner tree, less nodes, less states to deal with, and economize on computation. And as long as we economize on computation, we can go longer, and we like that. So iterative deepening can be enhanced by pruning states at the end step look ahead, at the nth layer, such that the end step look ahead cost is far from minimum. In other words, when we reach this layer here, we obtain the d plus j tilde values of the different states, and we're interested in small values. So those states that are far from the minimum, we prune them. And after we prune these states, we can prune more states at the next layer. And we prune as we go. Prune states at layer n before pruning states at layer n plus 1. Now, in doing so, we economize on computation. However, we run the risk of over pruning. Some pruned states may be pruned in error, may be good, may turn out to be good in hindsight. So what do we do in this case? Should we go back and check for over pruning? And how do we do this? These are questions to be dealt with, perhaps systematically, perhaps in some more heuristic way. Are there any questions? Okay, here's another form of pruning. We're going to enlist rollout to prune. Remember, rollout does this basically, goes forward, disregarding states as we go along. So even if the state space is very, very large, rollout is not bothered very much from that because it only looks at one state at each stage. So here is how this will work. We have, again, the current state, the various layers, and the last layer, and we select some level of look ahead L bar, okay? We will look at all the states in L bar, and from these, we're not going to do a full-fledged dynamic programming algorithm, but instead we're going to do an approximation. We're going to approximate the optimal trajectory from each of those with a rollout trajectory. And in the end, we're going to reach some of the states in layer L, and then we are going to add to the costs of the trajectories to those, we're going to add J tilde, and then we are going to find the one that has minimum sum of trajectory cost plus J tilde. So instead of solving the L-step look-ahead shortest path problem by iterative deepening, pruning, forward dynamic programming, we solve it approximately using rollout with some level of look-ahead. Now, this base heuristic here may have no relation to J tilde. J tilde may hide within it some rollout, but this rollout is not related. Hence the name double rollout. There's one rollout here and possibly a second rollout afterwards. And the two may not be related. And notice some special cases. Suppose we take L bar to be 0, okay? Then what we obtain is just one step look ahead truncated rollout. Basically, at x0, we look at all the successor states and run the base heuristic from there. And it's exactly the same as a rollout that's truncated at the level of L. On the other hand, if we take this L bar level to be lower at L minus 1, then there's no rollout. It's exactly the same as if we did L-step look-ahead approximation in value space. So this double rollout scheme is intermediate between truncated rollout and no rollout at all. with just plain approximation in value space. And there are variants of this approach. Here, this rollout can include modifications such as a simplified version of rollout, a fortified version of rollout, parallel rollout, where you use multiple heuristics, and it may also include iterative deepening, whereby we apply this to some level over here and then go to a lower level and to a lower level and so on. Okay, so this is another form of pruning. It's a different type than the type I described in the previous slide. Now, here's another algorithm that is based on this idea of looking at some states exactly with exact dynamic programming and some states with approximations. But instead of using this particular subgraph, it uses a more irregular, a less regular graph. And I call this incremental multi-step rollout. It involves a more flexible form of pruning and also a more flexible form of iterative deepening. Now, the difference from double rollout is the following. In place of the graph of the first L bar layers, we use a less regular graph, this blue graph, which is given here. It involves these nodes and the blue arcs. That's the graph. At each iteration on the way to constructing a trajectory, we have this subgraph, and then we look at the leaf nodes of this graph, and we calculate this thing here. D sub x is the shortest distance from x0 to x within this graph, going through the graph. In other words, for the purpose of calculation of shortest distance, we prune out all the rest, and we consider just the subgraph S. And we find the shortest distance to each one of the leaves through this graph. And we call this D sub x. And we find a leaf node x star that minimizes the shortest distance to the plus h of x, where h of x is a heuristic distance, okay? Some extra number that may involve also j tilde and may involve also the arcs that follow from x. And I'll give you an example of this in the next slide. So that's the idea. Given at any one step, we have a subgraph like this blue graph here, and we look at the leaves and we calculate the shortest distance to the leaves plus a heuristic distance to the end. And then we find x star that minimizes this, and we expand the graph by adding the successor nodes from x star. And then we start the next iteration with a bigger subgraph S all the way until we reach the layer L. So here there is pruning involved because this graph will extend and extend and extend. It will reach sometime layer L, but all these other nodes will be effectively pruned. And the criterion is going to be the expansion, and also, which is also going to be based on this sum. Okay, I'm going to explain this slide shortly in the next slide, but are there any questions at this point? Okay, so here are some details. This is the same pictures that I had in the previous slide. The current state, the various layers, a subgraph. We want to calculate a path. to the last layer, starting from the current state. And to this end, we have a subgraph which we extend until we reach the last layer. So at the start of an iteration, we have an acyclic connected subgraph S, which is rooted at x0. It is connected, so we can get to any leaf node. There is a path to go there. And it's also acyclic. It doesn't involve, okay, everything is acyclic here because the original graph is acyclic. There's only one direction of the arc from top to bottom. So we minimize this sum over all the leaves, and then we expand the minimizing node. Now, this minimizing node may be this, or maybe that, maybe that. Any one of these leaves can qualify as being the minimizing node. So sort of expand selectively. Depending on which one we expand, which node we expand, depends on h of x, the heuristic distance. And here's an example of heuristic distance that makes some sense. H of x for a given x, a given leaf node, is the cost of three things. The cost of a base heuristic that starts at x and ends at some node of layer L. So this is like the rollout. But we add also J tilde, the terminal cost approximation. And also we do something else. We add an extra term that favors paths with few hops. Like, for example, a term that's delta, sum delta, times the number of hops from x0 to x. So if x is here, the number of hops is 1. If x is here, the number of hops is 2. If it's here, the number of hops is 1, 2, 3, 4, 5, okay? Right? 1, 2, 3, 4, 5. So the further down a leaf node is, the more penalty there is going to be. So this term here, and depending on the size of delta, is going to favor paths with few hops. And this allows the possibility of making, after the graph expands down, this addition of this delta term allows us to backtrack, makes the nodes in higher levels more favorable. Now, some of the other aspects, the computation of the shortest distances is done progressively with a forward dynamic programming algorithm. In other words, once we have the shortest distances within this subgraph, then after we expand it, we can trivially obtain the shortest distances to these expanded nodes simply by doing a backwards calculation here. And as I mentioned earlier, the delta term allows the algorithm to backtrack, go down for a while, and then return back because this penalty becomes large. And for delta equals 0, what happens if delta is equal to 0? Then we get the maximum amount of pruning. The subgraph tends to be long and skinny, okay? It has basically only one path plus some neighbor nodes of the nodes on the path. So it's a very skinny path that goes down to the end. On the other hand, if delta is equal to infinity, then we get the minimum amount of pruning, no pruning at all, because we have to go from the nodes in layer n, we have to complete all of those before we can go to layer n plus 1. Because going from layer n to layer n plus 1, it costs us an additional delta. And if delta is infinity, that means that we have to go exhaustively through each layer before we start going into subsequent layers. So the delta parameter controls the way this computation is structured. For delta equals 0, we get a rollout, essentially, assuming that the base heuristic involved here is, okay, that we have this base heuristic involved here, and also perhaps there may be some other heuristic inside J tilde. So for delta equals 0, we get something like rollout. For delta equals infinity, we get the full dynamic programming solution without any pruning. And we still get the benefit of iterative deepening because this computation is progressive. And once we reach the limit of our budget constraint, of our computational budget constraint, then we can stop the computation and simply take the best node within the subgraph that we currently have. So this is the incremental multi-step rollout, and it fits within this landscape of multi-step look ahead with as long as possible a look ahead, using ideas of pruning, iterative deepening, and so on. And like I said, these ideas are relatively new. They are you can find details in your class notes, but they're the kind of ideas that are very well suited for term papers. And I know that many of you computer science majors that are in the class have experience with deterministic search algorithms and programming games and things like that. So it would be a very interesting type of term paper for you to try some of these ideas on projects that you're familiar with, on problems that you're familiar with. Are there any questions? Okay, since we're going to switch to a different topic, we're going to take a break, a 10-minute break, and then we'll take another break for 5 minutes at some other point. And you can ask me questions about the preceding slides when we come back. And according to my watch, we're going to get back at 5:22. Okay, we're going to go now into constrained rollout for deterministic problems. There's no constrained rollout algorithm for stochastic problems, by the way. It just doesn't work. So what I'm going to do is give you a brief outline, and then we're going to play a video from last year's lecture. So the main ideas here is to apply rollout to problems that have additional constraints over the entire optimal trajectory, constraints that couple the controls of different stages in ways that dynamic programming that cannot handle. Of course, dynamic programming can handle everything, but you need an elaborate reformulation in order to deal with the additional constraints on the whole trajectory. Now, by being able to deal with problems like that, we greatly expand the range of applications of rollout. In particular, we'll see that it applies to intractable discrete optimization problems. For example, shortest path problems with a limit on the number of hops. It's a very simple example. Shortest path solution from an origin to a destination is an easy problem, can be solved with many fast algorithms. However, if you introduce some additional constraints, like the path from the origin to the destination cannot have more than four arcs, okay? Now the problem becomes very difficult if you introduce a constraint like that, or similar constraints. These are the kind of constraints that we're going to try to deal with constrained rollout. Now, constrained rollout is similar to unconstrained rollout. Remember, in unconstrained rollout, when we are at a certain state, at the current stage, we consider Q factors. All the Q factors correspond to the different controls. And then we calculate these Q factors using the base heuristic. In constrained rollout, we exclude from consideration the Q factors that correspond to constraint violation. It's a very simple idea. And it turns out that cost improvement is still guaranteed of the base heuristic under some additional conditions. In particular, modified versions of sequential consistency condition or sequential improvement condition. You may need a fortified version in order to guarantee cost improvement. And also, there's an assumption that the base heuristic is feasible, generates a feasible trajectory, one that satisfies the additional constraints. And that can be a problem in some contexts. The base heuristic from the starting state might generate a feasible trajectory. So that's the point where I want to start the video with an example, a traveling salesman example. I'm going to begin with an example that you know and love. This is our four-city traveling salesman problem that involves travel costs, which are shown here. The numbers are, I think, pretty much the numbers we have been using. We have been trying to obtain the unconstrained minimum cost tour. A tour is a trajectory from A through the cities and back to A. And the unconstrained minimum cost tour is this one here. Now, suppose that there are some constraints here. In particular, there's a safety constraint that we have to obey. And each tour has a safety index or cost associated with it, which is numerical. And we require that we're required to find the minimum cost tour out of those tours that satisfy this constraint, where the safety index is less than 10. So this will disqualify this tour, which happens to be the optimal. It will disqualify another tour, this one here, and the other tours are allowed, okay? So out of those that are allowed, we want to find the best one. So how do we deal now with this extension of the problem? Okay, so let's review the unconstrained rollout algorithm and see at what point we have to modify to deal with constraints. Remember that the algorithm constructs a sequence of trajectories. In the case of the traveling salesman problem, it's a trajectory is a tour, starts from the initial state and ends at the final state through a sequence of controlled selections. And the rollout algorithm constructs a sequence of trajectories, one at each of n steps. And these trajectories under a sequential improvement condition have a monotonically non-increasing cost. And that's really the core of the theory, that in this way we are able to look at trajectories that go from beginning to end, have vision, but also decrease the cost as we go along. In particular, we decrease the cost if we start from x0 and use a heuristic. Now, at any stage k, the trajectories from k onward, they share the same initial portion. In other words, at the time k, we have already selected k controls, and we have gotten from the initial state to this state x tilde k. And now we look at all possible next controls, and we run the base heuristic to generate candidate trajectories, which correspond to the different controls that you can apply. So at x tilde k, we have this trajectory tk, which is the cost, which involves this initial portion plus the remainder that's completed with the base heuristic. And then we construct candidate trajectories that go up to xk the same way, and then we get a choice of uk, and then we run the base heuristic, and we find the candidate trajectory that has minimum cost, okay? out of all those here is the one that has minimum cost. First stage cost plus the cost of the base heuristic. And under the sequential improvement condition, we have that each time the new trajectory is no worse than the preceding one. And in particular, the last one, the one obtained by rollout, is no worse than the initial trajectory, which is the trajectory generated by the base heuristic. So now, as we generate these candidate trajectories, when we have constraints, some of these candidate trajectories may not satisfy the constraint. So the remedy is very simple and fairly obvious. In order to deal with the trajectory constraint, we discard all the candidate trajectories that violate the constraint, and we choose tk plus 1 to be the trajectory that is best out of the ones that satisfy the constraint. It's very simple. We get a number of trajectories, some of them violate the constraint. We throw away the ones that do and do the best we can with the others. And we still maintain, obviously, this property here, as long as we can always find at any xk that we generate, we can always find a candidate trajectory that satisfies the constraint. In other words, as long as we don't make some choices that are irredeemable. Once we move here, we cannot find that feasible trajectory anymore. So we have to guard against that eventuality through assumptions or modifications in the structure of the algorithm. So this is the constrained rollout algorithm. And I'm going to illustrate now with the traveling salesman problem. Oh, I'm sorry. I have one more. And then and let me ask for questions. Are there any questions?
I have a question.
Yeah.
What if the trajectory generated by the base heuristic itself violates the constraint tk? What do you do then?
The first one, T0, you mean?
Yes.
T0. It's an assumption that that the base heuristic starts from, generates a feasible trajectory.
All right.
From the initial condition, okay? We have to make some assumptions because everything else is pretty general here.
Cool.
Are there any other questions? Okay, so this is the basic idea, and now we're going to formulate the problem precisely. We consider a deterministic optimal control problem with this system equation, and we define a complete trajectory to be a sequence that goes from 0 to the initial state to the final state. And we have a cost function that's very general. It depends in an arbitrary way on this trajectory. And we also have a constraint that the trajectory is one out of a given constraint set of trajectories. So this is as general as it gets at this point. Now, the problem is that with constraints, coupling stages like that in an arbitrary way, and cost also coupling stages, we can't rely on going state by state because we may have made in the beginning some choices that may affect choices far into the future. So we turn to the idea of state augmentation, and we redefine the state to be at time k the partial trajectory, everything that we have chosen so far. And now this partial trajectory evolves according to a dynamic system, like so. The new partial trajectory is obtained from the old one by adding u, k, and by that. Somebody say something? Okay, I guess somebody should get himself or herself muted. Okay, so the new trajectory, partial trajectory, time k plus 1 is obtained from the old by adding the controller, by adding the new state. And now the problem becomes to minimize the final state of this system subject to a final state constraint. So in this way, we don't have this, this coupling across stages where the cost function involves previous states. It only depends on the final state, and the same thing for the control. So this is one trick that we use in order to redefine the rollout algorithm to deal with these couplings across stages. And here is the algorithm. We start at the initial state, and we keep adding controls and states up to the point where we get to x tilde k, the kth stage. Then we have generated this partial trajectory, this y tilde of k. And now we extend this partial trajectory by one control and one state. We extend y tilde k to obtain all these partial trajectories that start from here and end up at these points here, okay? We add uk and the corresponding next state, and we do this for all feasible controls. And now we run the base heuristic from each one of those. Now the base heuristic generates a partial trajectory, r of yk plus 1, okay? This one here, and so on. And now we join this part with this part, and we do it for every uk. We join the partial trajectories yk plus 1 and ryk plus 1 for all the different values of uk, and we obtain complete trajectories of this kind. Okay, so we have now these candidate trajectories. Some of them are feasible, some of them are not feasible. So we calculate the set of controls for which this trajectory here is feasible, satisfies the constraint of the problem. And out of those thinned out set of partial trajectories, we find the one that is best, the one that gives you the minimum value of cost. But we minimize not over all controls, but only over the controls for which I get feasibility through application of the base heuristic. Are there any questions here?
Yes, Professor, I had a question for you. In the past, we had talked about problems where we augmented state to take into account time delays. Is this essentially equivalent to those running rollout from those kind of augmented problems?
Yeah, it's the same idea. Not exactly the same, but it's the same idea. Augment the state in order to take into account couplings with previous states. It's the same idea. Okay, so let me now demonstrate the algorithm using the traveling salesman example. This is the same one that we had at the first slide. We want to minimize find the tour that minimizes the travel costs, okay, given by this matrix, but also meets the safety constraint, and two of those tours do not meet it, okay? So we have the cost function, we have the constraints, and we also have a base heuristic. And this base heuristic, of course, the base heuristic can be anything. And I've drawn here with blue. So at state x0, the base heuristic generates a complete trajectory. And it's this one here, okay? However, the base heuristic, when it is at this partial tour, is not sequentially consistent. And instead of generating this trajectory, it generates this trajectory, okay? Now, I did this because I wanted to make the example have more variety. I'm free to do that because, like I said, the base heuristic can be anything. Also, the base heuristic from this partial tour is this blue here, okay? Is this heuristic from AB. It's heuristic from AC, the heuristic from A, and the heuristic from AD is this one. How about the other tours? Well, the heuristic from ABC, it's this one, right? Because there's no choice. Similarly, the heuristic from ABD is this one. There's no other choice, and so on. So I have indicated here the heuristics from A, AB, AC, and AD, and not from the other partial tours because there's no choice. It's implied what the base heuristic is. Okay, so we're going to go through constrained rollout step by step now. This is basically the algorithm of the previous slide. And we start at the initial state, and we will do rollout at A. How will this be done? We consider the partial tours A, B, AC, and AD. We consider this partial tour, and this partial tour. And then we run the heuristic from each one. From this one, the heuristic gives me this. That's a candidate, okay? From here, the heuristic is this one. And from this one, the heuristic is this one. Now, this one happens to be infeasible, so we just throw it away. And we compare this tour and that tour. And the one that wins is this one. So we move from A to AB. That's what this bullet says. We start at A, consider the three possible choices, and we obtain, by using the base heuristic, we obtain these tours here, ABCDA, ACBDA, and ADCBA. Discard this one as being infeasible. Compare this one, and find this one here to be better, and we select AB. So we're now done with the first step of rollout. Is this clear? Is there some question? Okay. So we have made this rollout choice, and now we move to AB, and we do rollout from here again. So what do? We consider this possibility and that possibility and run the base heuristic from each one. Okay? Now, this trajectory here is infeasible because it violates this constraint here. So we throw this one away and we select this one. In other words, we move to ABC. That's what this bullet says. We consider the partial tours ABC and ABD, run the base heuristic to obtain the complete tours ABCDA and ABDCA, and we discard this one as being infeasible, and we select the complete tour, this complete tour. Of course, to be entirely formal, and we have to go from here to here, but there's only one choice, so I'm not showing the completion of rollout. This is the rollout choice at AB, this is the rollout choice at ABC, this is the rollout choice at ABCD. And we have reached the terminal state, and we have the rollout trajectory. Okay, is this clear? If we did not have this constraint and we did not have this, the violation from these two tours, the rollout would choose this trajectory, which would be the optimal unconstrained trajectory. However, because of the constraint, this was recognized at this point here, and we went the other way. Okay, so now let's go back to theory. What are the properties of this constrained rollout algorithm? Well, obviously, we will need notions of sequential consistency, sequential improvement, and so on in order to be able to assert anything. So there are extensions of the definitions of sequential consistency. Sequential consistency is the same as the sequential consistency of the unconstrained version. Now, sequential improvement is a little different. As part of the definition, we require that the set of feasible controls, the ones from which the candidate trajectories do satisfy the constraint, we assume for sequential improvement that the set of feasible controls is non-empty. In other words, at this step here, there's at least one out of those trajectories that satisfies the constraint. So that's the sequential improvement condition. First, that the set of feasible controls is non-empty. There's at least one that is feasible. And moreover, out of those that are feasible, the Q factor of at least one, the minimum Q factor over those, is no larger than the heuristic cost from here. Okay. Now your notes have this. Your notes have the details of this, but I'm just summarizing this here. In other words, it's the same kind of definition for sequential improvement as before, except that this property here of minimum heuristic Q factor is no larger than heuristic cost at point tilde is satisfied with a minimum taken over the ones that are feasible. In other words, we just discard the infeasible trajectories and we define sequential improvement in a natural way. Now, a lot of things can go wrong if the sequential improvement condition is not satisfied. In particular, there may be no feasible trajectory. You went merrily along here, but all of a sudden you've realized that you reached the point where you can't satisfy the constraint anymore. So to deal with this, there's a fortified version whereby once you find a feasible trajectory, you keep it for later, just in case you can't find another one that's feasible. Moreover, you replace it with a new trajectory once you find one that's better in terms of cost. So for the case where sequential improvement is not guaranteed to hold, it's not known to hold, we use this fortified version, which maintains a tentative best trajectory and follows it up to generating a better trajectory through rollout. And now we restore the cost improvement property, assuming that the base heuristic generates a feasible trajectory starting from the initial condition. In other words, if our initial trajectory is feasible, then with this fortification, we're guaranteed to always follow a feasible trajectory and one that has no worse cost. The details of this are a little tedious, but they're natural, and you can guess them already by just looking at this bullet if you think a little bit about it. Okay, so there's a multi-agent version also, which I'm not going to go into the details. The multi-agent version applies for the case where each control has multiple components, okay? And therefore the search space is very large. So what we do in this case, we play this trick of reformulating the problem with the control space unfolded so that the components are chosen one at a time. And then we apply constrained rollout on this equivalent reformulation. So this extension is natural, is simple to deal with. We simply, each one of these decisions is broken up into M decisions, where M is the number of agents, and then we go one step at a time with the base heuristic and all this procedure here that I described. Okay. So now let me return to the traveling salesman problem. This picture is exactly the same as the one that you saw in the previous slide. There's a cost function associated with the travel costs. There's a safety constraint, a constraint that for the trajectories. There's a base heuristic, which from each partial tour completes the partial tour. Let's look at the issues of sequential consistency and sequential improvement. Okay, is the heuristic sequentially consistent at A? It's not, and why is that? Somebody? Why is it that this heuristic is not sequentially consistent at A? At A, it generates this trajectory. Once it goes through the first step, it generates a different trajectory. Well, that violates sequential consistency. Is the heuristic sequentially improving? Well, we have to check two things. Whether from every one of the partial tours, it can find a feasible candidate trajectory. And indeed, this is so. At AB, it can find this trajectory. At A, it can find this trajectory. At AC, it can find this trajectory and that trajectory also. And at AD, it can find this trajectory, but not this one. This one doesn't qualify. So the feasibility requirement for sequential improvement is satisfied. But there's another requirement for sequential improvement, namely that if you run the base heuristic from any given partial tour, if you run the base heuristic from some partial tour, it's this one here, and there is a neighbor such that running the base heuristic from that neighbor gives you a better or equal value. And it turns out that this is true for A, and it's true for A, B, C, and A, B, and AD trivially. Why? Because this tour here has a cost of 27, whereas the base heuristic has a cost of 28. So the sequential improvement condition is satisfied at A, and it's also satisfied at the other nodes fairly trivially because of the simple structure of the graph here. So we have sequential improvement, and indeed the rollout constructs this trajectory with cost 27, which is better than the cost of 28 that the base heuristic constructs from the beginning. However, if we were to change this one travel cost and from 20 make it to 25, then the sequential improvement condition at A would be violated. Why? Because when I compare this with that, I find that I compare this with that one, I find that this one is worse than that. This one is also worse than that. Okay, look at the numbers here. And also this one is worse than that. This one has cost 45, whereas this one has cost 28. So if I were to change this one number, then the sequential improvement condition would be lost. And in that case, you would have to resort to the fortified algorithm, which whenever generates a new trajectory, it compares it to the best tentative that you have, which in this particular case is the initial trajectory. And if you apply fortification to this example, you'll see that the rollout algorithm at A tries to find a better trajectory, but it cannot. The reason is that this one is worse, and this one is worse, and this one is worse, or infeasible in this particular case. So it sticks with the heuristic trajectory, with the trajectory that was generated at A, and rejects this one. So that goes back to the question that was asked by one of you. I'm not sure who was that. What happens if what happens if the heuristic is not feasible from the initial state? Well, you have to assume that. And you have to assume that to prove anything. And if that is not, if that is assumed, then by fortification, you're guaranteed to get a better or no worse trajectory than the one that the heuristic generates from the initial state. Now, okay, there's one more thing. How do I find a base heuristic that generates a feasible trajectory from the beginning? Sometimes this is very hard, but we just skip this question and we just assume that you have a base, that we have a base heuristic that at least from the initial state, it can generate a feasible solution. That's part of the assumption for this problem. Are there any questions here? I went slowly here, and also in terms of pictures, to give you the opportunity to follow all the steps. I didn't see any reaction from you, so that can mean one of two things. Either you got very bored with the details and tuned out, or the slides are so complicated that that you lost track of what's going on. But anyway, since there are no other questions, I'm going to go forward and summarize where we are. Okay, a constrained problem, constrained deterministic problem, and the rollout algorithm for it involves some ingredients, all of which are quite general. Okay, some of you are saying that it's very clear. Thank you for the details. So I'm glad to hear that. Okay, so what are the structural components of the framework that we have developed so far? First of all, we have trajectories, which are defined by a graph, a layered graph showing the transitions from states in one stage to states in a next stage through the use of controls. So this there is this optimal control graph that we're using, and the assumptions here are that the problem is deterministic and is also finite state and control. We will not be able to go through all this argumentation that of the previous slides if we had an infinite control space. We have a finite control space and a finite state space. And we have a graph that defines the transitions. So this is the dynamic system defined by the graph. And we have a cost function that can rank trajectories, either numerically or possibly through the use of an expert. We may have an expert that we ask, given this trajectory and that trajectory, which one is better? And the expert has some kind of way of rank trajectories. So we have a cost, but we'll just assume that we have a cost function, a very general cost function. We have a very general set of constraints, which you can check. We assume that you can check it and determine feasibility of the trajectories. And we have also a base heuristic that starts from a partial trajectory and completes it, generates the remainder to form a complete trajectory. So these are the ingredients of our framework. The problem structure, the dynamic system rather, the cost function, the constraints, and the base heuristic. And now, once I give you the dynamic system, I give you number one, then the other choices are independent of each other. I can choose anything I want, and this does not have to depend on that. This does not have to depend on the other two. Moreover, given 1, 2, and 3, which is the problem, you can try several different base heuristics, or you can combine the heuristics into a super heuristic, whereby, which naturally chooses the one that has minimum cost out of the ones that are feasible, okay? Some of the base heuristics for a given, from a given partial tour, a given partial trajectory, may not be feasible. So you discard those and use and check and compare the ones that give you feasible trajectories, and then pick the one that gives you best cost. So you can have multiple heuristics, combine them together, and all of these choices are independent of each other. So given a particular type of problem, there are a lot of different problems that correspond to it, and also a lot of different base heuristics, and therefore rollout algorithms that can be used. So that's the constrained rollout algorithm in structure. And now I'm going to look at a particular type of problem involving discrete optimization. So here's the problem. It is very general and very useful. An awful lot of optimization just has this structure here. The problem is to minimize a general cost function, g sub u, subject to u lying within some constraint set. And the only thing that we assume here, other than finite control space, finite choices for u, the only thing that we assume is this component structure. U has multiple components that we arrange from 0 to n minus 1 in the way of stages. So the problem is laid out, the problem structure is laid out like so. We have seen this graph before. There's an artificial initial state. We choose the first control, and the states of the first stage are these. Stage 2, they are these pairs. Stage 3, triplets, and so on. The last stage marks the completion of a solution. These are all partial solutions. This is a complete solution. And it has a cost g sub u, okay? This cost enters here. Now, if we didn't have these constraints, then we could, this would be a shortest path problem, okay? If we had costs only on the arcs, this would be a shortest path problem. But now we have constraints, and some of these trajectories are feasible and some of them are not. So we have to pick our way out from the beginning to the end while maintaining feasibility. Okay, so that's the problem. And we can view it as a special case of a constrained deterministic optimal control problem where the states are not really significant. And they're just artificial, just a single state at every step and only controls. And a single state which is equal to some artificial x0. So for problems where states do not have some kind of intuitive meaning, we may prefer to sort of abstract them out of the problem and use this type of formulation. On the other hand, the range of problems of this is just enormous. Any kind of combinatorial optimization problem that you can think of, matching, routing, assignment, scheduling, bin packing, any kind of problem, including the very difficult ones that are NP complete and so on, fits this framework. As long as you have this component structure, and you usually do, okay? Furthermore, any integer programming problem can be put into this framework. In integer programming, we have some variables which are disused really, and they can take a value that's integer, usually 0 or 1. So in an integer programming, in a 0-1 integer programming problem, the solution is a sequence of zeros and ones. And I'm going to give an example shortly. Now, because this problem is a special case of the one we had before, not really a very narrow special case. Actually, this problem is equivalent to the deterministic optimal control problem that we had before. But we can view it as a special case in the sense that there's only one state. Because this problem is a special case, we can apply the rollout algorithm that we saw up to now. And this is the way to provide an entry point for reinforcement learning into the solution of discrete optimization problems. What we're doing here is allowing the use of methods of approximation in value space, approximation in policy space, dynamic programming. We allow these methods to come into this broad range of problems. And now, as I said, this is a very, very broad class of problems, and there are many, many methods for solving them. For example, random search is one such methodology, where you start from some initial feasible solution, and you generate at random a collection of other neighboring feasible solutions, and you move to one that looks promising, and then you search at random within a neighborhood of the place where you are, and you find another solution that's promising, and so on. And of course, you can do this in many different ways, and intelligent ways in particular. But in random search, you go from a complete solution to a complete solution, and then to another complete solution. You don't go from a partial solution to a less partial solution up to a complete solution, which is what we do in rollout. So random search and rollout are quite different in their structure. And this is true also for other methods, local search methods. In local search is like random search, moving from one solution to a neighboring solution and to another neighboring solution within some neighborhood. And the method is defined by the neighborhood and by which you move, which candidate within the neighborhood you select. Again, these local search methods have this complete solution structure. You go from a complete solution to another complete solution and so on. You don't build up the solution component by component. Genetic algorithms are another popular class of combinatorial discrete optimization methods. And again, they have the same kind of property as random search and local search. You operate on a sequence of complete solutions, and you go from one solution to another solution by generating some candidate successors through mutation, extension. There are various operations that you can apply. And okay, if you have some intuition about your problem, you can generate interesting ways to interesting neighborhoods from within which to search. And these algorithms have their successes and also their failures. And they are important classes of algorithms, but the main thing is that rollout is different. Integer programming also has a large variety of a rich methodology. And the part of integer programming that's closest to rollout is branch and bound. I don't know if you've heard this method. I'm not going to describe it here, but it involves fixing integer variables one by one and finding which candidates to fix in some intelligent way using upper and lower bounds and so on. That bears some similarity to what rollout does. So rollout is different. Is different better or worse? I don't know if it's better or worse, but it is good to have different algorithms because these algorithms are flaky and sometimes they don't work. So it's good if your algorithm, your favorite algorithm, does not seem to work, to have some alternatives to try. So now let me go to an example. This is an integer programming problem. It's one of the classical ones. It's called the facility location problem. And I'm going to go slowly. There's a lot of formulas here. So you can ask questions if something seems to be unclear. Okay, so what do we have here? We have some candidate locations in which we want to place facilities, like power plants, if you're talking about electric energy production, or some other kind of facilities, service centers. And there are some candidate locations, and we want to find the most promising locations. So if you place a facility in location K, then UK is equal to 1. If you don't place a facility, then UK is 0. So placement of a facility at a particular location corresponds to a 0, 1 integer variable. Now, these service centers, these facilities, are set up there in order to satisfy some demand, satisfy certain clients. These blue circles are clients that are going to be served at these facilities. And these clients have a certain demand. Client I has demand DI for services. And this demand can be satisfied at a location K at a cost AIK per unit. And a client can actually split his demand between two centers and send a piece here and a piece here. Similarly, in other words, there's infinite divisibility, we assume here, of the demand of a client between the various service centers, the ones that are up, of course, that are operating. Okay, back to facilities. If we place a facility at location K, then we provide capacity CK. CK is the capacity of a facility at location K. And it also has a cost BK. This is cost to set it up, okay? And UK takes the value 0, 1, depending on whether a facility is placed at K or not. So this is the overall constraint structure, and the cost is a linear cost. Okay, this is a bit of a handful. There's a cost for services. This is the service cost. And there's a cost AIK for unit per unit of client I that is served at facility K. So this is a linear cost that depends on the Y's. The Y's are variables also, okay? Optimization variables in addition to the U's. There is also a linear cost that penalizes the placement of facilities. If you build a facility at location K, you have to pay a cost BK. And if you don't build a facility, UK is equal to 0, so you don't have to pay that cost. So this is a linear cost function in the variables Y and in the variables U, except that the U's are not infinitely divisible and they can take only the value 0 or 1. And what are the constraints here? Well, of course, we have the integer constraints that the use can only be 0 or 1. And the service allocation and the facility assignments must be such that the total demand is satisfied. In other words, these Ys have to be services have to be non-negative. They should add up to the demand of client I. So for every client, the portion that allocates the various facilities should add up to the total demand Di. So we have this constraint, this constraint, this constraint here, and also the constraint that at location K, at facility K, assuming the facility is built at location K, this can only serve demand up to a level Ck. In other words, the total demand that's being served at location K should not exist Ck if Uk is equal to 1, and no demand can be satisfied at location K if there is no facility that we have built at location K. Okay, so this is the classical version of the problem, but we can make it even more difficult. There may be additional constraints on U, but we will ignore for the moment. But let me give you an idea of what these additional constraints can be. Okay, let's go back here. This is the definition of the problem and a transcription into our standard form of minimizing G sub U over U belonging to C. What is C now? The constraint set is the set of all the U's that are in 0 or 1 and also can satisfy the demand and perhaps some other constraints, like some public policy constraints, like zoning constraints.
I'm not
like,
sure.
Did I hear someone? Zoning constraints that say that within a certain geographic region, you cannot build any facilities, or you can build only one facility and no more. And so there may be groupings of locations that have special properties that are not shared by locations in other places. This is what we mean by public policy constraints or additional constraints. But let's not worry about those, although our methodology can address those, okay? Which makes it, which adds to its generality. So this is the constraint set of the problem, and this is the cost function of the problem. Now, okay, here's the cost function. I told you that it's this one. However, if you look at this problem and you look at the variables U and the variables Y, you realize that the really important variables are the U variables. If I give you the facility locations, then the remaining problem is a linear programming problem that can be solved very quickly. It's what's called a linear transportation problem, okay? It's a classical network flow problem that is can be solved in polynomial time by very efficient algorithms. So if the placement variables are known, the remaining problem is easily solvable. So we are going to formulate our problem in terms of the difficult variables, and the others, the Y's, are going to be determined automatically through this optimization, where H is the set of all feasible demand allocations, the ones that are non-negative, and satisfy the constraints. So once I fix the U's, the constraint set of this problem is determined, and this problem becomes a linear programming problem, and its optimal value, I'm going to call it G sub U. In other words, I have eliminated the variables Y from the problem by saying, well, they're automatically determined once you determine this location variables U. Okay, so now I have the problem in the way I want it. I have a cost function involving a sequence of decisions, and I have a constraint set, and I can check whether for a given sequence of decisions this constraint is satisfied. And now I'm going to apply a rollout whereby I will first pick the variable of the first location. Do I build or do I not build at this location 0? Then I go to location 1. Do I build or not build? And so on, go all the way up to the last one while applying some kind of Bayes heuristic and checking also for constraint satisfaction. So are there any questions?
Is this an example of a problem where certainty equivalence has been applied? Because I would assume that the DIs in general are random variables, but in this case, we're just treating it as some known constant, right?
Okay, this is a deterministic problem. Now, how you have arrived at this problem, we don't examine here. It may have been the result of certainty equivalence. In other words, there may have been some random variables here. For example, this demands DI, okay? They are random, and they probably are changing over the calendar year. But we assume here that they have been replaced by deterministic quantities. So we're using, in a practical sense, we are using certainty equivalence. However, from a mathematical point of view, we assume that these are known. They're not random. Does that answer the question?
Okay, yep, thank you.
Okay. Okay, so now we are going to apply this constrained rollout algorithm, considering places one location at a time. That means we first fix U0, then U1, and so on. So at stage K, we make the placement decision UK from 0 to 1 at this location, and there are n altogether stages. And here's our Bayes heuristic. I could use any of a number of Bayes heuristics, but here's the one that I'm going to be using here. The Bayes heuristic completes a partial trajectory, right? So given a partial trajectory, it must have a way of completing this trajectory with additional U variables. And it chooses to place a facility in all the remaining locations. In other words, having fixed U0 up to UK, there are two candidate trajectories to consider. One is where we set the next facility to 1 and all the remaining facilities to 1, according to this Bayes heuristic. And the other candidate trajectory is not to place a facility at the next location, but that place a facility in all the other remaining locations are as per our Bayes heuristic. And now at U0 up to UK, we have two candidate trajectories, and we check for feasibility. And this one is going to be feasible. Why? Because it builds up everything, okay? If we have reached up to here with a state feasible so far, we're going to remain feasible because the Bayes heuristic is very generous and allows us to build a facility in every location. On the other hand, this one may not be a feasible trajectory because this indicates that we do not place a facility in this location, and this location may be a critical one. This particular, and without building it, then we can't satisfy the demand. Okay, so we looked at these two. And depending on which one yields feasibility and minimum cost, we move to UK plus 1. It may be 0 or it may be 1. And now we note that because of the nature of this Bayes heuristic, sequential improvement is satisfied. The reason is that, feasibility is satisfied because of the particular choice of the Bayes heuristic, and also, it's easy to see that the minimum Q factor between these two has to be less than the Q factor of the cost of the Bayes heuristic starting from this location. Basically, the Bayes heuristic here is not only sequentially improving, but given feasibility is also sequentially consistent. In other words, it stays the course. You start out with a Bayes heuristic that sets all to 1, and then as you move forward, it continues. The tail of the trajectory generated by the Bayes heuristic also consists of 1s. So it's easy to start to verify that sequential consistency is satisfied and also feasibility is satisfied. So you get cost improvement over the initial choice, which would be to build everything, build a facility in every location. That's what the what the Bayes heuristic would give you starting from the initial state. So trivially, you get cost improvement, and generally this algorithm, in my opinion, works pretty well, particularly since it can handle some very, very difficult constraints, which would not be possible to handle with other methods, like integer programming type of methods. Okay, are there any questions now on this example?
I have a question. So setting dynamic programming aside for a second, if I'm just looking at this problem as an integer or linear program, I would be finding like the total number of variables I would be finding values for would be all of the U1 through UK, or all of the UK values, but also all of the Y sub IK values, right? Like, yeah. Okay, so this cost function has two parts. It has trying to minimize the demand and also trying to minimize the number of facility locations that you're going to put down in total. So you said that, so we have our control space corresponding to only putting down facilities or not. And then you said once you have a facility assignment, then at that point you feed the rest of it into a linear program to figure out what is the best way to allocate the demand, right?
Yeah.
Okay. And so we've seen before that, like, for example, in the case of the linear quadratic case, that sometimes your controls can be continuous as well. So I guess my question is there any way to adapt this framework to just purely solve a linear program where, for example, if your controls were in some continuous range 0 to 1? Because I know we've seen that before.
The answer is that would lead you to a different kind of methodology. Branch and bound, so major methodology in integer programming, as I mentioned, does this. In other words, branch and bound at any one state allows, at any one point, has variables that are fixed to integer values, and also variables that are free to take values in the range from 0 to 1.
Okay.
So there is this feature of relaxing the integer constraints and solving corresponding linear programming problems in branch and bound. In rollout, that's not done.
Okay.
We treat the variables as 0 or 1, and the remaining variables are automatically determined by solving this linear transportation problem, minimizing this objective here, subject to these constraints.
Okay.
So we always operate with integer variables. And that's the difference. That's an important difference between this methodology and the branch and bound integer programming methodology.
Because if, for example, if your y variables were restricted to be integers, maybe not 0 or 1, but 0 through 10 integers, they could also be a part of your control space, couldn't they?
They could, yeah. It's all a question of whether you can solve this problem here easily or not.
Mm-hmm.
If the y's are not restricted to be integer, then this problem is very simple to solve relative to, relatively speaking.
Right.
However, if there are additional difficult constraints on the y, which make this problem non-polynomial and hard, then you're faced with a different type of animal, and you have to treat it differently. And you have perhaps to consider simultaneously the choices of uk and yik. But because here this problem is simple, relatively speaking, you can follow the solution methodology that we have discussed. There's something else about these transportation problems. They tend to have integer solutions under some conditions. So even though we have assumed here that the y's are fractional, could be fractional, in reality, if all the other data of the problem is integer, then these transportation problems also have integer solutions. Okay, that takes us into different territories, and I'm not going to go any further.
Okay.
But there's one thing that I want to mention, and it's the last bullet here. There are a lot of transportation problems here, right? For every new value of u, 0 or 1, you have to solve a transportation problem. And on the other hand, these transportation problems are similar. They have similar data, and then you can use the solution of one transportation problem to hot start the solution of the next transportation problem. And there are algorithms in network flow theory, network optimization, this auction algorithm in particular, that are very well suited to hot starts, starting the solution from an already good solution. And these auction algorithms are very suitable for as intermediate solution methods for obtaining the values, the cost values.
Okay, thank you.
Okay, so we have reached the end of the lecture. The material of today's lecture is covered in greater detail in your textbook, the Lessons from AlphaZero textbook that you can find from my website. And now in the next lecture, we are going to do stochastic rollout type of ideas. Today we covered deterministic rollout, and the next time we're going to look at stochastic rollout and the Monte Carlo tree search methodology, which is like a pruning type of methodology, but it applies to pruning the simulation of that's involved in stochastic problems. Then we're going to discuss an extension of rollout to the case of infinite spaces problems, in particular an infinite number of controls. Everything that we have said so far applies to a finite number of controls. And that will prepare the ground for going also into multi-agent rollout 2 lectures from today. Now, as I mentioned earlier, this is a good time to think about your project. Today's material should provide good inspiration for some of you, also in the next lecture, but particularly the first 4 lectures, which were introductory foundational lectures for our course. I urge you to think about your project And I encourage you to get in touch with me by email and to make appointment to talk by Zoom. If you have some ideas that you're not sure about. And we ask you to send a one-page or less proposal about your term paper. We want you to start thinking about your project, and we want you to have a proposal ready by the end of the spring break. And send it to me to take a look. And that applies to both mini research projects as well as the read and report type of projects. And also, if you have some difficulty narrowing down a project, then or you need some help with finding some good papers to read, please send me email and I'll try to help you. So that's it for today, and we will see you next week.